So in the previous class, we saw pastries, how they used to generate or to derive a word. And we saw the concept of the leftmost derivation and the rightmost derivation, that is just a methodology of doing things, but they come down to one and the same thing, right? Then now we want to look at regular languages in the context of context-free languages, right? We already saw that we can generate a regular expression from a CFG, meaning we have already come across regular languages that, or context-free languages that were also regular languages, right? So we want to explore that space a little bit more and find out what or how it shapes out to be and how big it is. Right. So in the textbook, there's theorem 19 that says all regular languages can be generated by context-free grammar, right? This makes sense because you've already seen on the diagram that I showed initially that regular languages are indeed a subset of context-free languages. Right? So theorem 19 then comes and says all regular languages are context-free languages, meaning for each and every regular language, there is a CFG associated with it. Right. So theorem 20 then says if all the production of a given CFG fit into one of two forms, right? Either we have got a non-terminal going to a semi-word or a non-terminal going to a full word, where the word may be null, right? Then the language generated by this CFG is regular. Right. We'll get to the definition of semi-word in a bit. But we are saying if all the production of a CFG are of these two forms, then we know that the language generated by the CFG is regular. I'll repeat this and I'll add something towards the end. If all the productions in a given CFGs are of the production, a non-terminal going to a semi-word or a non-terminal going to a full word or a full string or to terminals only, then the CFG is regular. We have guarantee that the CFG is regular. We can call it regular by simply looking at it. Right. It is also possible that a regular language, the CFG that a regular language is in, may not be in this format, but the CFG describes a regular language. Right. Another way to look at this is the following. For every regular language, there exists a CFG in such a way that a non-terminal, or in such a way that all the productions, right, are of the form a non-terminal going to a semi-word or a non-terminal going to a full word. Right. That's another way to look at it. All right. So examples of semi-words. So for a given CFG, a semi-word is a string of terminals, maybe none, concatenated with exactly one non-terminal on the right. Right. Exactly one non-terminal on the right. So examples of semi-words, if you have got AAS is given here, terminals and exactly one non-terminal on the right. Right. You can have S going to X. So this caters for maybe non-terminals concatenated with exactly one non-terminal on the right. Then we can also have full word, right? All these three make up what we call semi-word. Right. So whatever you do, just realize that everything else is a terminal except for the rightmost element, which is going to be a non-terminal, right? So that's a semi-word. Right. So something that is not a semi-word, ASB is not a semi-word, right? BXAB is not a semi-word, right? But BABX is a semi-word. All right. So that is how we identify semi-words. Right. So let's look at examples. Find CFG that generates the language on the given regular expression. So we're given a regular expression and they want us to find the CFG. Right, a methodical way of doing this is to first convert this regular expression into a finite automata. Right, so by doing, we can see that we've got an initial state where we can have an A, and we can have an A, and we can also have another A, and then we can get to a final state. The initial state is also a final state, and then we can also, so if you leave here, you can also have another A, and then you've got triple A's, right? And then from here, right, after A, you can also have a B. So you can start with a B and go to a final state, right? If you have an A at this point, you can then go here and then another A, another A. If you have a B at this point, you can then come over here. And then if you have more B's, you can have them over here. So for each of these, we have an A and a B, an A and a B, an A and a B. This is for this one. Over here, we have an A and A. We need a B, so you can have B's going here, B going there. Right, so you can have a looping state like that, A or B. All right, so this is the FA. From here, all you need to do is to name them. So I'm going to name them. This is going to be S. I can name this in now. I like A, B, C, D, and I can name this E. Then what you see is that I'll have S going to the transition and then the state. So with an A, I go to the state, right? Or the transition B, I go to D, right? Then all final states are also labeled as you're going to put a noun, like that. Then we go to A. A with an A goes to B, and with a B it goes to E, and then A, that's it, right? B with an A it goes to C, with a B it goes to E, then C with an A it goes to A, with a B it goes to D, and it is also a final state. D with an A it goes to A, with a B it stays in D, and it is also a final state. Then lastly, E with an A it goes to E, with a B it goes to E, and it doesn't escape. So we can see that all the productions of this CFG are semi-words, right? A and the non-terminal, A and the non-terminal, or they are terminals which are given by noun. So this fits into the notion that we are describing right now. Right? So a regular language has got a CFG, corresponding CFG, and that CFG can be given in the format of a semi-word or full word. Right. So that's it. Otherwise, if you don't go through this methodical approach, you can simply use your head to get it. So I can easily come and say S goes to A, S, or B, S, or now. I could also do this. These two have got the same equivalence. They produce the exact same number of words and are all correct. So it's just a matter of which one you are much more comfortable with. Right. Next, let's look at this one. Find the regular expression generated by the CFG. Right. So now I want to find the regular expression. Right. So semi-word, terminal, semi-word, terminal. So this is simple enough as it is already, right? So you can have S can produce S and A and B directly. So you can have A, or you can have a B. Right? Other than that, you can have an AX. So we see AX, right? So other than that, you can also have, you've got an A that keeps on producing A's, right? So we can have, I can say an A plus, right? Or BS, so I can have B. So this B is going to have, we can generate a lot of B's. So what's going to happen? We've got BS, 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 BS. So it can keep on giving a number of B's, right? Right, you can have as many B's before, not twin star. Rather, I want to put a plus because it means you've got at least one. We can have B's, and then after that, you can then be followed by A's, like that. So this is the full spectrum of things, right? So this is the regular expression for the given language. All right. Sweet. Now let's move on. We have the last one here. We are given a CFG that's not in, of which the productions are not all semi-words and full words, but they want us to give, they are guaranteeing us that this is a regular language, and they want us to give a CFG that shows it is a regular language. So we have to generate another CFG that produces the exact same language as this one, but it's got semi-words and terminals only. Right, so XRZ, AX, ARY, BY, and so forth. So we need to understand what the language is. So S is going to X, R, and Z. X, we see that X is A or B, clean star. R is AR, BY, so we have got AR and B, BY. Right, so R, you've got A's that are looping, and then you also have B, Y, right? I don't think it's supposed to be Y, it's supposed to be R, right? But let's just take it to be R. So in that case, it will mean that if it is R, it will also mean that this is A or B, clean star. And then we've got AZ, Z goes to AZ, which means it is a clean star, right? So we just need to write it to represent this. We just need it to write it to represent this. So this and that can be represented by one statement. So let's say I start with S goes to AS or BS. I don't want to say S. AX or BX. Right. The next question becomes, is now accepted in the word, right? X can go to X can go to now, R can go to now, Z can go to now. So now is accepted, right? And then after that, I now define what X does. So X is AX, we can have BX, and it can also go to now. And then we also want a scenario, we want to define Z. Right, if you have a word, right, right, Z says the words that are here, when Z is not going to now, then they end with an A, which, to be honest, is already covered here, words ending with an A, right? But those that are ending with a B are also catered for, but we can just put something for a Z, right? So let's say, we can then say A, Z, then we come to Z, Z goes to AZ, or it goes to, if it goes to B, it goes to BX, and then it can also go to now. By doing this, we have given a CFG that produces the exact same language, but is in a form that is easily recognizable as a regular language. All right. So let's take a break and we meet each other in the next video.